Welcome to Spring LIB.
Alrighty, so we got a projectile, and let's just start with the information that's given to us. We know that the initial position of our projectile, I want to say r of 0, it's at the origin. So we just have it at the origin, at the beginning. Both x and y are equal to 0. And we know that the initial velocity, which I'll place right here, v0 equals 12 meters per second in the I direction, and plus 49 meters per second in the j direction. And that's the initial velocity. And so you have both your x and your y component right off the bat from this velocity that's given to us. We also know another important fact about projectile motion: your x initial is going to be equal to the x component of velocity the entire time. That won't change, which is a convenient thing about projectile motion. And then regarding our y component of velocity, this is going to be equal to the initial velocity, which we actually have conveniently right here, the initial velocity, and minus, so we're fighting gravity, we have to do a minus gt. All right, and the x component of the position, we can find that very conveniently by doing one of the first equations you learn in kinematics: x equals velocity in the x direction times time. The y component of the position, we can find it by using one of our very old faithful kinematic equations: velocity in the y direction times time, minus, since we're fighting gravity, minus 1/2 gt squared. All right, and we can find the projectile's distance, horizontal distance, magnitude of that, by using just good old Pythagoras. If you just take your components, you square them both, you can find that radial distance over time. So now what we have to do is substitute values into all these equations, and when you do that, you can get a ton of different values and you can make a table, which is what we did here. I'm going to pull that out here so we can take a look at that. There we go. So we make a table, and here you can see we have our time from 0 to 10 seconds. Velocity in the x direction, you can see, stays constant the whole time. Velocity in the y direction, beginning positive, and then you can see it becomes negative after it reaches the max height. Then you have your position over time in the x direction, which just stays positive the whole time, increasing from 0. And then for the y direction, or the y position, you see it increases from 0, gets to its max height, and then decreases. And then the radial position, you can see, conveniently matches the x motion for the most part here. You can see it travels all the way across and ends at the 120 as well. And that's just a vector that is essentially tracking the whole motion. So it's not going to be the same as the x, but it's going to have that same starting value and ending value as the x, as you can see there, with the 0 on the top and the 120 on the bottom. All right. Now we want to also consider something here. We want to consider the fact that the velocity is not perpendicular to the displacement when the distance is maximum. So there's only going to be some component in the velocity along or opposite to the direction of this radial vector. This component of velocity will either decrease or increase the value of our magnitude of our radial vector, and it cannot be maximum. So this means the velocity vector must be perpendicular to r. I can actually write that like this: the velocity vector has to be perpendicular to r. That's perpendicular to r when the magnitude of the radial component is maximum, is max. Important fact there that we need to work with. All right, so now at this point we're going to start with what we were given here at the beginning. We had our initial velocity, And we had our acceleration, which we know I can write my acceleration here. Acceleration equals minus 9.81 meters per second squared. And we want to consider the magnitude of the displacement vector will be maximum at time t. So let's use this here to describe. Let's box this out of here, and we'll do velocity equals v naught plus acceleration times time. And we can plug in what we know for this. We already know what the initial velocity is, and we know what the acceleration is. We just have to make sure we put a minus in for the acceleration, and then we're going to be able to have just time left over. So we will get v equals plugging in the v naught here, this vector first, and then plugging in the acceleration second, and cleaning it up. So we'll get 12.0 in the I direction, plus, using my parentheses here, we have 49.0 in the j direction, minus the 9.81 meters per second squared times t, also in the j direction. So that's why we have these guys grouped here together. And we can also do a displacement vector, doing a v naught t plus 1/2 at squared. And when you plug in all the stuff that we have for that, we have the initial velocity vector right here. And we also know that the acceleration is the negative 9.81 meters per second squared. So when you plug all that in and you go ahead and clean this up, we look at something of the nature of r equals 12.0 t I hat plus 49.0, which is the j, times t, minus the 4.9, which is just part of the 1/2 of the acceleration, 4.9 t squared. And this is in the j direction. Now, at maximum displacement, the velocity and the position vectors are perpendicular. Hence, the dot product will be 0. Very important fact here. V dot r at maximum displacement, the velocity and position vectors here are perpendicular. So these guys are 0. We'll do the dot product. So I'm going to move this over to here. And we can build this up here, this dot product here. So 12i plus our 49 minus 9.81t and of course we have this full thing. I'm going to just box this in right here. We have a dotted dot product with our radial vector, which we found here. Oof, really running out of space there. And this is, of course, in the j direction, this last guy. And then when you run through this dot product, when you run through it, you find that t equals 0 seconds, 5.69 seconds, and 9.3 seconds. Lovely. Now the displacement at 0 seconds and 9.3 seconds are actually the minima. And so the maximum displacement occurs actually just at this middle one here, this 5.69 seconds. All right, so we want to substitute this value of t into the equation of displacement, which is this equation right here. And what I'm going to do, I'm actually going to take my my lovely table and move this to the side so we can actually have some more space here. Put that right there. All right, so we're going to take our R equation here, or R, and we can now plug in the 5.69 seconds in each one of these. That's in the I direction, plus the 49 times 5.69 minus 4.9 times 5.69 squared. All right, and then when you do this, we can figure out both components, which is 68.3 in the I direction, and 120.2 in the J direction. And if you want to find the magnitude, we will use the same thing over here, what we've looked at before. So the magnitude of the radial vector being the 68.3 squared plus the 120.2 squared. And then you want to take a root of this. And you're going to get roughly 138 meters. Now, just to kind of build on what we just did here, I had to use the fact that for maximum displacement, the velocity vector and the displacement vectors are perpendicular. So that's the whole reason why we had that dot product, the v dot r down here, is we had to use that fact about the orthogonality, essentially, or how they're going to be perpendicular at those specific points. Now, if two vectors are perpendicular, we know the dot product is 0. So first I had to consider that at time t, the displacement is going to be maximum. And then I calculated the displacement and the velocity at t. And then I took dot product and set the dot product equal to 0 since they are going to be perpendicular. And then we were able to solve for time. And then knowing time, we were able to plug it into our radial expression and then find both components, the x and the y components, and then go and find the magnitude here, which is what we did.